In this highlight video, we will discuss the regioselectivity of elimination reactions. We'll start out by defining regioselectivity, and after you've watched the video, you will be able to predict the products for elimination reactions of unsymmetrical alkyl halides. What is regioselectivity? Well, let me show you using a couple of examples. Let's look at the top example. If we're doing an elimination reaction, we have a secondary alkyl halide, we have a strong base, so this would be an E2 reaction. Remember that we can label the position where the bromine is attached as the alpha position, and elimination can go to either or any available beta positions that bear a proton. So here's a beta position here, and here's a beta position over here. So elimination can go to one side to form a cyclohexene. We could show it to the other side as well, but of course these are both the same. So in the E2 elimination of bromocyclohexane, we only have one possible product. So there's no selectivity that's possible. Let's look at the second example. Here again we have the alpha position where the bromine is attached. We have a beta position here and another beta position here. If we eliminate a proton on the beta position to the left, we get this product over to the right. If we eliminate the beta position on the right, we get this product that is drawn on the left. So what's the relationship between these two molecules? They're not the same, right? These are constitutional isomers, right? They have the same molecular formula, but they have a different connectivity of atoms because the double bond is in a different place. So, in a reaction where more than one constitutional isomer is possible, but one or some of them are produced in excess, that reaction is said to be regioselective. So in this reaction, what we'll learn is that the product on the left will be the major product. So we can say that a reaction is regioselective if it can form more than one constitutional isomer as product, but one or some are produced in excess. All right? So the way you can think about this is in this molecule, the double bond is in two different regions. In the first one, the region goes this way. In the second one, the region is over here. And this reaction selects for the product with the double bond in this region. So it's regioselective. Regioselectivity of elimination reactions is described by Zaitsev rule. And that says that when an elimination can yield more than one possible product, the more stable product is formed in excess. So let's look at the example shown here. Again, we have a secondary alkyl halide. We're using a strong base, so this should be what mechanism? This should be an E2 mechanism. We have two beta positions, one over here and one over here, and so we have two possible products, the one with the double bond on the end and the one that has it internal. So, which of these is more stable? Okay, for alkenes, the stability is related to the amount of substitution that the double bond has, or the number of alkyl groups that are attached to the double bond. If we look at this first product, we notice that there's only a single alkyl group attached to that double bond, so we call this one mono-substituted. The second product has an H here, but it has a methyl there, a methyl group, and a methyl here. This one would be called tri-substituted. And the trend is that as we increase the number of R groups or alkyl groups attached to the alkene, we increase the stability. All right, so here is mono-substituted, and over here is tri-substituted, and we see that tri-substituted is more stable than mono-substituted, and so this one here would be our major product, as described by the Zaitsev rule. Let's look at two more examples. The top example, let's look at the alkyl halide. We have an iodide. What's the substitution? This is a tertiary alkyl halide. And ethanol is going to be our base as well as our solvent. And so this is a very weak base. And so the mechanism should be E1. Still, it's going to follow Zaitsev rule, and so we have to consider our different possible products. So we have a beta position here, a beta position out here on this methyl group, and another one over here. Of course, the one on the left and the one on the right are equivalent. They're related by symmetry. So if we do the elimination to either of those, we get one product. If we do the elimination out to the methyl group, though, we get a double bond that is pointing off of the ring like this. So which of these would be more stable? All right, so we look at the amount of substitution. This one is tri-substituted because it has 3 alkyl groups attached. This one over here would be di-substituted, and we know that the tri-substitute is more stable, so this would be our major product. One more example. Again, we have a tertiary alkyl halide and a weak base, giving us an E1 mechanism. We have a beta position here, one here, and one here. The two methyl groups are equivalent, so they would only give a single product. And if we eliminated to one of those, here's the two methyl groups, we get the elimination product would look like this. If we eliminate it to the beta position on the left, our product would look like this. Okay, so again, di-substituted, tri-substituted, this one is going to be more stable. In addition, the one on the right, because the double bond is adjacent to the benzene ring, this one can also have resonance. So that would make it even more stable. So this would be the major product.